We are now going to talk about the binomial theorem. Binomials, hopefully you remember that a binomial, by definition, is a polynomial that has two terms. For example, x plus y to the n. Terms are separated by pluses and minuses. So that's how we can tell there are two terms here, and we're raising that x plus y binomial to the nth power. So let's raise these binomials to different powers. In other words, what I'm doing is I'm substituting in for n, and I'll start with my first positive integer, 1. X plus y to the first power is simply x plus y. Fairly easy so far. X plus y squared is simply x plus y times x plus y. Our idea here is that we're going to do first, outer, inner, last, or the famous FOIL from your Algebra 2 days. So when I do first, I do first term of this binomial times first term of this binomial, x squared. Outer, I'm going to multiply the two outer terms of the two different binomials, plus xy. Inner, I'm going to multiply the two inner terms of the separate binomials, plus xy. And finally, last, the last terms of my FOIL, I'm going to multiply y by y to get y squared. So I have x squared plus 2xy plus y squared. It does take me a little time, but I can do it. X plus y to the third power. Now I've replaced n with 3. So this is x plus y times x plus y times x plus y. Well, good thing from our previous expansion of this binomial, I know that this is x squared plus 2xy plus y squared times x plus y. The way I like to multiply a trinomial times a binomial is as follows. X squared plus 2xy plus y squared over x plus y. And when I multiply them, I'll take this first term and multiply it through. So x times x squared is x cubed plus x times 2xy is 2x squared y plus x times y squared is xy squared. Then I start over. Y times x squared is x squared y. Notice what I do is I immediately group the like terms together. Y times 2xy is plus 2xy squared. And finally, y times y squared is plus y cubed. Now, I add these two together to give me, well, this will come down, there's nothing to add here, plus 3x squared y plus 3xy squared plus y cubed. And we can see I'm taking up a whole board now just to do to the third power. So I've expanded x plus y to the n by substituting n equals 1, 2, 3, 4, 5, and 6. Of course, we could keep on going, but I barely was able to squeeze in the sixth power here because you can see that I'm increasing the number of terms. Well, that's one of our takeaways. One takeaway is there are n plus 1 terms for x plus y to the n. So whatever n is, if I add 1 to it, I'll have the number of terms. When n is 1, I have 2 terms. When n is 2, I have 3 terms. When n is 3, I have 4 terms. When n is 4, I have 5 terms. When n is 5, I have 6 terms. When n is 6, I've got 7 terms. You can see that I had to stop at 6 because I don't think I could write small enough and clear enough to squeeze in x plus y to the 7th power. So whatever n is, add 1 and you'll come up with the number of terms. Let's look at the exponents. I have the first term and the second term. Look what happens to the exponent of the first term. It goes 1 and then I could write here that this is x to the 0 power. And I could write here that this is y to the 0 power. So in this simple expansion of x plus y when n is 1, you can see x is to the first power and then x is to the 0 power. So the first term has a descending pattern of exponents. Start high, go low. And when I say low, we're going to stop at 0. Remember, anything to the 0 power is 1. So a to the 0 is 1. Conversely, I start low and go high. It's an ascending pattern for the second term, y in this case. So I have y0, then y1. Let's just look at the x's, the first term. x2, x1, nothing written here, x to the 0. Here, x3, x2, x1, we could write x to the 0 here. Here, to the fourth power, x4, x3, x2, x1, x0. To the fifth power, 5, 4, 3, 2, 1, 0, x to the 0, I could write that in. To the sixth power, 6, 5, 4, 3, 2, 1. Conversely, let's take a look at what's happening with y. Well, this first term is x squared y to the 0. I don't have to write that. I'm just doing that for instructional purposes only. And then it goes y0 and then y1 and then y squared. How about here? It's y0, y1, y2, y3. y0, y1, y2, y3, y4. y0, y1, y2, y3, y4, y5. Notice I stop wherever the exponent equals whatever n this is. So because this is 6, I know I'm going to stop where y is to the 6th power, which is equal to my original n. Let's also look at the sum of the powers. Well, the sum of the powers will be n. For example, here n is 1. Look at the sum of my powers. 1 and 0 on this term. Remember, terms are separated by pluses and minuses. 1 plus 0 is 1. 0 plus 1 is 1. How about here? 2 plus 0 is 2. 1 plus 1 is 2. 2 is equal to 2. Here, 3 plus 0 is 3. 2 plus 1 is 3. 1 plus 2 is 3. 0 plus 3 is 3. On any term, the sum of the powers will be equal to whatever the n is. Here, x plus y to the 6th. Let's take this term. 3 plus 3 is 6. 2 plus 4 is 6. 1 plus 5 is 6. 6 plus 0 is 6. No matter where you go, the sum of the two powers will equal whatever n is equal to. And finally, let's look at the pattern of the coefficients. Here we have some symmetry. Let's look at x plus y to the 6th. 1, 6, 15, 20, and 15, 6, 1. You can see that whatever happens over to this side, to the left of 20, happens to the right side. Here, with an even number of terms, if n is 5, I know I have n plus 1, 6 terms. 1, so when I say 1, there's nothing written there, but we can assume there's a 1 there. 1, 5, 10, 10, 5, 1. We have this symmetry, kind of like you're going up a staircase and then back down. Here, x plus y to the 4th, 1, 4, 6, 4, 1. So we have this symmetry. And how do you find those coefficients? Well, we're going to use the binomial theorem to find those coefficients.